of V, this means it has to mean you let dA act on V. That's the only thing it could reasonably mean. And so since this holds for all V, lo and behold, omega is dA wedge A transpose. So if we have the attitude matrix, we can calculate the connection forms directly by this. Now, you also have a homework problem about coframes. Don't be scared of these. They're actually really, really simple. There's something amazing that's about to happen. So what is the coframe? Well, the coframe is just what it sounds like. It's the frame which is dual to the set of one forms which are dual to the given set of vector fields, in the same sense that like dxi is dual to partial xj, right? This is the dual basis to partial xi is the dxi's at each point, right? So dx1, dx2, dx3 is the coframe to the Cartesian frame. Likewise, theta1, theta2, theta3 is our notation for the coframe of the E frame, meaning that this happens. Proposition, if you have a vector field and you've got a one form, you can expand the vector field by you can calculate the components by the coframe acting on the vector field. We've seen this before in n dimensions. We've looked at this in our previous discussion of tensors. All right, this is just special to our current discussion. To calculate the components, you can let the dual vectors act on the vector that picks off the component, right? And to pick off the components of a vector field of a differential form, a one form, we let the one form act on the basis, and that gives us the component of the one form. Same thing here. And the point is that that's still true for the E frame. Yeah, left the reader. What's perhaps interesting, though, is that if you have the attitude matrix to relate the Cartesian frame to the E frame, the same attitude matrix relates the coframe to the Cartesian coframe. In other words, I can straight away write down for the spherical frame over here that theta 1 is equal to cosine theta sine phi dx plus sine theta sine phi dy plus cosine phi dz, and theta 2, I guess upper one, theta upper 2 is, cosine theta cosine phi dx plus sine theta cosine phi dy minus sine phi dz, and theta 3 is minus sine theta dx plus cosine theta dy, if you like. Now, of course, that might not be the most natural thing to look at. Like, it might be more natural to think of this as actually being what? I mean, I think this is actually also just d rho. This is actually d rho. And if memory serves me correctly, this might be rho d phi. And I think this is probably rho sine phi d theta, maybe? Those are chain rules, if I did them right. Let's bet I did them right. Let's go on. So this brings us finally to the kind of main event of this story arc of the course, which is Cartan structure equations. So Cartan structure equations, what they say is that if we look at this E frame and the coframe theta, we can look at them as a vector of one forms. Theta is a vector of one forms. I can look at d zeta as my vector of the Cartesian differentials, right? And so the attitude matrix relates the coframe to the Cartesian coframe, the differentials. But this can be written simply as a matrix multiplication. This is theta is, this matrix column multiplication of forms. matrix of functions. This is a one form, this is a function, this is a one form. We got one form equals one form, makes sense. And it turns out that d theta is omega wedge theta, and d omega is omega wedge omega. These are equations, these are Cartan's equations of structure. And we can derive these equations from the matrix calculus with considerable ease, actually. So I've put the derivation of these like on the test in here before, or on the final exam, I can't remember. Because you can actually do it. Like, do not give up. Like, watch along, it's not hard. It really isn't. Whenever I ask these kinds of things on the final or the test, they tend to come with like a very lengthy preamble, right? Because I don't assume that you memorize all this stuff, obviously, right? So we have previously derived that omega is dA wedge A transpose for the attitude matrix. We also know that the attitude matrix is orthogonal, which is A transpose, which of course the wedge in here is kind of like, wedge is just multiplication in this case. And that's equal to the identity matrix, right? On the other hand, I also know that theta is A d zeta. So d theta is the exterior derivative of this business, which is going to give me dA wedge d zeta plus A d zeta. But of course we know that d squared is 0. Ooh, that's gone. On the flip side, we also know that A transpose times theta is equal to A transpose A d zeta, which is to say that d zeta is A transpose theta. So d zeta is A transpose theta. But, oh, wait a minute. dA wedge A transpose is omega. So omega wedge theta. Oh, there you go. That's it. What's interesting is that these equations are the Fresnel-Ray equations. When you apply these equations to the context of restricting your frame to a curve. Like, it's the same, the Fresnel-Ray equations are a particular instance of Cartan's equations of structure. Now d omega, again, we just exterior differentiate. D squared is 0, so that's gone. This over here is a little bit trickier because we have dA wedge dA transpose. Now you be careful, dA transpose is not the same as like just dA transpose because we have that, you know, A transpose A is I, so when we take the exterior derivative of that, it gives us this plus that is 0, which tells me that dA transpose is actually minus A transpose dA A transpose. And when I plug that in down here, I get two minuses, which give me a plus. I got dA wedge A transpose, and I got dA, I got omega wedge omega. So it's actually pretty simple. Now, so that is general. And by the way, I think if you study what we did, there's nothing particularly three-dimensional about what we just did. That easily could be adapted to n dimensions and looking at an n frame. There's no calculation we did which actually rested on, like I talked about the cross product, but did I use that in any of the general stuff? I did not. All right, so as long as you had an orthonormal frame in Rn, the equations of Cartan could be derived just the same. I just made it three-dimensional because I'm following O'Neill and try to keep it simple, believe it or not. So if you study the differential geometry of surfaces, you're asking the same question that we're asking with curves, which is when are two surfaces actually the same surface in disguise? When can I take one surface and just like do a, you know, like a rigid motion, move the one surface over to the other? When do they have the same shape, right? So essentially that question is, I think, answered more or less by the shape operator. If they had the same shape operator, they would have the same shape, roughly speaking. But what is the shape operator? Well, if you have the unit normal to the surface, you define the shape operator to be the covariant derivative of the unit normal in the v direction. And it turns out that you can prove that the shape operator is in fact a linear transformation on the tangent space. It turns out it's a symmetric linear transformation, which means that it has real eigenvalues. The real eigenvalues are called the principal curvatures. The product of the principal curvatures are the Gaussian curvature. The sum of the principal curvatures divided by 2 is the so-called mean curvature. So these are K and H. These things were studied by Gauss. It turns out, and you say a surface is flat, if its Gaussian curvature is 0. As I was telling you guys last time, this is part of a larger story, the Gaussian curvature being the most simple implementation of the Riemann tensor. It's vanishing being tantamount to the space being flat. So surface is flat if it's got vanishing Ricci scalar, which is the Gaussian curvature. Surface is minimal if h is equal to 0. That has to do with like soap bubbles and variational problems and so forth, but I say this is an extrinsic property because the Gaussian curvature actually is not due to the way this surface is embedded in space. It is a property of the intrinsic geometry of the space itself, whereas the trace, the mean curvature is part of the extrinsic geometry. The ultimate theorem that you want to understand in the study of elementary differential geometry is the Gauss Bonnett theorem. It says that the total Gaussian curvature of a compact orientable geometric surface M is related to its Euler characteristic. So we've talked a little bit about Euler characteristic before, right? And we saw how that was connected to the Betti numbers, to the homology, ultimately to the cohomology if we believe Rentlen. This says now that it's also connected to differential geometry. That the sum, whatever this means, this Gaussian curvature, it is what it sounds like. You integrate the Gaussian curvature over the surface. This is a two form. We integrate the. So just to show and tell here for a minute. Here are the formulas that Gauss looked at back in the day. You know, we had. I sometimes call it like alphabet soup. You have this E, this F, this G. These are the dot products of the partial velocities of the parameterization of the surface. Ultimately, they're kind of like how you build the metric on the surface from those. And after some suffering, you come to formulas for the you also introduce the LM and N, which have to do with the second derivatives of the partials. And so to calculate the Gaussian curvature, you just have to calculate M, L, N, E, F, and G and calculate these quotients. Easy peasy. Just like that, right? Or you could do the calculation like I did last time, where you find the coframe to the surface, you calculate the wedge, you calculate the differential, you figure out the connection forms on the surface, right? And then calculate the exterior derivative of the connection forms, and that is proportional to theta 1 wedge theta 2. That proportionality constant is the Gaussian curvature. So it's so far removed, these two worlds of calculation. These are the classical formulas. This, there is something to see here though. There's something called a helicoid. A helicoid has E equals to 1, F equals to 0, G equals to that, because of these calculations. And there's also something called, oh man, I don't have the catenoid. Dang it. Well, here's a cylinder. So the parameterization of cylinder, the Gaussian curvature for cylinder is 0. The mean curvature is not 0. Because the cylinder is curved, right? But it's not intrinsically curved, because if you were to imagine yourself on the cylinder, the geometry you would experience as a ant or whatever would be a flat geometry. Unless you walked around too far and got back to where you started. That would maybe be a hint something funny was going on. Here's the curvature for the saddle surface. There's really cool formulas for orthogonal patches. I still don't understand where that formula comes from. Let's see here. So this right here, it turns out that there's a helicoid, there's a catenoid, and they're rather different looking, but they actually have the same E, F, and G, which means that because that's basically what goes into calculating the Gaussian curvature, they have the same Gaussian curvature. So these two rather different surfaces have the same local geometry. And this is actually a mapping that takes you from one to the other, I think. I have a picture of it to show you. That link there no longer works. That link is broken, unfortunately. So So this is just a description of how we integrate on the surface. Give me a second here, I'm fishing for something. If we calculate the total here's some calculations for like the total Gaussian curvature. Integration of KdM is, if K is constant, it's just K times the area of the surface. So like the total Gaussian curvature of a sphere is actually 4 pi. And the total Gaussian curvature for a torus is 0. The total Gaussian curvature of a catenoid, minus 4 pi. They're all integer multiples of 2 pi. All right, curious, right? So this can be understood in terms of Gauss map. Let me get to the point here. I may need to, sorry guys. I'm in the wrong, maybe it's over here. I got too many tabs open, obviously. All right, so let me get straight to the punchline. Well, I guess the punchline was back here. Oh, sorry. So this is the big theorem, ultimately, that connects differential geometry to, well, I don't, So it turns out that the integral of the Gaussian curvature over a patch, a 2-segment, which is like a kind of curved rectangle, it turns out to be the integral around the boundary of the rectangle, something called the geodesic curvature, plus these angles, which are the exterior angle at each vertex. So you know, you have to get into it to understand all this, but it takes me about a week or so to really explain. But once you have all it, you get really, here's the proof of it. Come on. It brings you to the, it ultimately is how you prove the Gauss Bonnett theorem, namely that the integral over the, the integral of the total Gaussian curvature of the surface is 2 pi times the Euler characteristic. Now this, my final point, is most interesting when we study its applications, which is my other final thing here. Where'd it go to? There. So if we have a triangle, all right, which is formed with geodesics. So what you want is you form a triangle where the sides of the triangle are what are lines to the surface. The geodesic is a generalization of the concept of a line because it's the line of shortest, it's the curve of shortest distance between 2 points on your surface. So a triangle that you're interested in should be formed by joining geodesics between 3 points on your surface. And it turns out, corollary to the Gauss Bonnett theorem is that the integral of the Gaussian curvature over a triangle is the integral of the geodesic curvature around the boundary of the triangle. And that works out to 2 pi minus the sum of the exterior angles, or the sum of the interior angles minus pi. So if the, what happens if your surface is flat? If your surface is flat, the Gaussian curvature is 0. The geodesic curvatures are 0. This is all 0, and we get the sum of the interior angles is pi. On the other hand, if your surface is like a sphere, it's got a positive Gaussian curvature. So this works out to something non-zero. And that says that the sum of the angles, interior angles, is larger than pi. On the other hand, if you've got negative curvature, the sum of the interior angles, less than pi. These are the 3 cases of geometry: flat, like spherical, or hyperbolic. And here's some sad pictures of trying to show you. I always think about this kind of triangle on the sphere. You can see that the angles are like bigger than, you could have like on the quarter of the sphere, it's like 90 degrees, 90 degrees, 90 degrees, you get 270. The weird thing about triangles in a sphere is the sum of the interior angles actually tells you how big the triangle is. Yeah, isn't that weird? Because like if you have 270, you can only get 270 if you're doing like a quarter of the sphere, right? If you've just got a little bit past pi, it's a much smaller triangle. And the same thing is true over here in the hyperbolic space. The deficiency from pi has to do with how large the triangle is. It's only a quirk of flat space that the area of the triangle is divorced from the interior angles. That's a special feature of flat space. Yeah. Anyway, this is of course not meant to be a complete course in differential geometry. I just wanted to show you that in fact we can use differential forms to calculate these things. And when you pair differential forms with the concept of orthogonal geometry, special things happen. This is part of a larger story called Cartan's calculus. And indeed, if you can find a way to put an orthonormal frame on an abstract space, you can understand the shape of the space. Anyway, I should shut up because my class is over. So sad. I guess I need to make you guys a test, huh? Yeah.